Okay, Algebra 2, welcome to Chapter 3.2, where you are going to learn about imaginary numbers, which are part of complex numbers. But before we get into that, we're going to review simplifying radicals, which we did a little bit in the previous section. So remember, simplifying a radical means that your final answer has no perfect squares remain under the radical. And the radical, again, is that symbol. So what is a perfect square? It's numbers like 4, 9, so that'd be 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, whoops, I lost 8 squared down here, 9 squared, 10 squared, 11 squared, 12 squared, 13 squared, 14 squared, you just flip, it's 169 versus 196, 15 squared. Those are the most common, as well as 25 squared. So it would be nice to be able to recognize those as a factor, and if you see them under the radical, you can pull them out as their square root. So let's start off with simplifying square root 120. Now a lot of people might go to 12 times 10, but you want to try and choose a factor. So we're going to write this as something times something, but try and get one of the factors to be a perfect square. So I see that 12, I know 12 is 4 times 3, so I'm going to go 4 times 30. And since 4 is a perfect square, it comes out as 2. And oddly enough, square root of 30 cannot be simplified. So that would be your final answer. Now we have square root of 48. And I know a lot of you might say 6 times 8. And we will do that in a second. But I'm going to show you a better way, because 6 times 8, neither one of those is a perfect square. You always want to try and find the biggest factor that is a perfect square. 48 is actually 16 times 3 as well. And that means this can come out as 4. You have the square root of 3, and you're done. But let's say you did do 6 times 8. So there's more than one way to do these. It's just that if you can go to the biggest factor first, it makes the problem a little bit shorter. So 6 is the same thing as 3 times 2. 8 is the same thing as 2 times 4. And so let's see how we can simplify this. We know that the square root of 4 is 2. We know that when you have twins, we talked about that in the last section, rad 2 times rad 2 is 2. Anyone that comes out gets multiplied together, and we still have the 3 here, and when you put it all together, you also get 4 rad 3. So it doesn't matter which method you use, but if you can find a bigger factor, it makes it a shorter problem, which means less chance for mistake. Okay, now we get to introduce the imaginary number I. Use your imagination, any of you SpongeBob fans. So this occurs a lot naturally in electronics. So to deal with when they get a negative under the radical, they are assigning it the letter I for imaginary number. And so that is our formal definition. Whenever you have a negative under radical, you can pull out the negative part as I. Now even better, if I square both sides of that, I would get I squared, and the square of the square root of negative 1, when I square that, is just negative 1, which means anytime we see I squared, we can replace it with the integer negative 1. So in application, what that means is if I see a negative x, the negative part comes out as I, and then I deal with the square root of x as I would any number. Now in simplifying radicals, there's sort of this cyclical process. We start off with I is the square root of negative 1, that's its definition. If I square both sides, as we saw, you get I squared equals negative 1, which is very handy. And if I multiply both sides of that by I get I cubed equals negative I. And again, negative I is like negative square root of negative 1. I actually prefer negative I for that one. And if I take the I squared and I square both sides of that, we get I to the fourth. Negative 1 squared is 1. And if you then multiply both sides of that by I, you get back to what we started with. So I to the fifth is equivalent to I. I to the sixth would be equivalent to I squared. And you would just keep going around the cycle. The most useful of these two is I to the fourth and I squared, because we can replace the I, the imaginary part, with an actual integer. So let's see this in practice. So we have here the square root of negative 16. So just to show the process in the beginning, and I know it'll go faster as we get along, that's like the square root of negative 1 times the square root of 16, which is I times 4, and we tend to write the number first, so that would be 4I. Here we have the square root of 24. So that is going to be the square root of negative 1. Now 24 is not a perfect square, so we want to break it down. So I do know that it is 4 times 6. I'd rather that than 8 times 3, since 4 is a perfect square. So I is going to come out from the negative 1. Square root of 4 comes out as 2. The rad 6 stays there. And in general, we write this as 2. You always write the number first, then the I, then the radical. You don't like to write the I after the radical, because then it looks like maybe it's underneath the radical. And so that would be our final answer there. Okay, so that's how you would simplify. Simplify the radical same way we normally do, but if you see a negative, it comes out as I. Now, how do I simplify I to the 21? So we're going to use some property of exponents here. I to the 21 is the same thing as I to the 20 times I to the 1. Right? Remember, you add your exponents when you multiply the base. And the reason why I chose 20 is I'm choosing the largest factor of 4, because I know that if I have a factor of 4, I can simplify it as 1. So this is how this is going to work. This is I to the fifth. Actually, let me write it this way. I want to go back and write that as a 4 times 5 is 20 times I. Well, we know I to the fourth is just 1 from our little circle. 1 to the fifth is still 1 times I, so this just simplifies out to I. So your goal is to pull out the biggest factor of or multiple of 4 that you can. So for 107, I can rewrite this as I, because we know 4 goes into 100, which means it goes into 104, and then this will be I cubed. So 104 plus 3 is 107. Since this one is a multiple of 4, it's just going to come out as 1, and so we're left with I cubed, which you can write as just minus I, based on our chart right here. Okay? Now, let's see why we even have these complex numbers. So, we're going to go back to what we were concentrating on in this chapter, which is factoring and solving quadratics. So, if I have to solve, and we're going to use the square root method, which, remember, means you want to isolate the squared term. That's our first step. And then we take the square root of both sides, but when you take the square root of one of the sides, you will include a plus or minus. So let's do this. So first thing we want to do is isolate this. So I subtract 4 from both sides. Then I go to take the square root, so plus or minus the square root. Notice we have a negative under our radical, so here I just have x. Here I'm going to have plus or minus. The negative part comes out as I. Square root of 4 is going to be 2. So my answer is plus or minus 2I. All right, let's try another one. And if you want, pause the video and try this one on your own. So again, we want to isolate our squared term. So the first thing is subtract 42 from both sides. Then we divide by 6 so that I have x squared equals -7. Take the square root of both sides. So those cancel. We have x equals, now 7 can't be simplified, but that negative is going to come out as I, and you have a plus or minus 7. Actually, how we usually write this is plus or minus I rad 7. The reason for that is this is not addition and subtraction. This is just a positive and a negative product. So I really discourage you from writing it this way. Put the plus or minus in front of everything. Okay? So now welcome to complex numbers. So a complex number is a number that's made up of a real part, which we're going to call A, and added to that is the imaginary part, which has the I on it. So A and B are both going to be real numbers, but the B times I makes that, so it's complex because it has a real and an imaginary part. So here's your real part, and this is your imaginary. In working with complex numbers, when you are adding or subtracting them, you add and you just basically combine like terms. In other words, the real number gets combined with the real numbers, and the imaginary coefficients get combined with the imaginary coefficients. So combined like terms. I can't talk and write, sorry. When you are multiplying, so when we're going to be multiplying complex numbers, you want to utilize the fact that when you're done, you can simplify anything that is I squared with -1. It basically changes the sign of your answer. And when we get into division, you're going to be using something called complex conjugates. And that means that if you see A plus BI, you will multiply it by A minus BI. So that's the same number, but with a negative or the opposite sign in between. So we'll see how that works when we get down to the bottom. All right, so let's start off with this. Here we have 6 minus 4i plus, so notice there is a plus here, so we're adding two imaginary numbers. So what I'm going to do is just take this second one and write it underneath this one so that we line up our like terms. And so 6 plus 1 is 7, -4 plus 3 is a -1, and that would be your answer. So you're just combining your like terms. Here again, I am subtracting. So to make this easier so we can line things up, I'm going to turn it into addition by distributing that negative to both terms. So I have a -5 and -1 times a -4, that makes that a positive 4i. And now I can add the two together. So 3 minus 5 is a -2, -2 plus 4 is +2, and then it's the same process. So just be careful with the negative, you do have to distribute it to both terms. Now we get to multiplication. So we are going to use our distributive property. So I'm going to have 4i times a -6 plus 4i times I. So how does this simplify out? Well, this gives me a -24i, and this I squared, so I have 4i squared. Remember that we replace I squared. Whenever you see I squared, it gets replaced with -1. So now when we write this as a complex number, we always put the real part first. So I actually have 4 times a -1, which is -4, minus 24i. And that would be our final answer. We always write the real part first. So the -4 minus 24i. So that was a simple distribution. Now we're going to do our whole FOIL process, first, outer, inner, last. So 2 times 3 gives me 6. 2 times a -2i gives me -4i. Then we have our inner, which is going to be -12i. And then our last terms, which is going to be a positive, 4 times 2 is 8. And then I times I will give me I squared. So just like before, you have 4 terms. You'll always be able to combine the 2 middle terms. So this will be 6 minus 16i plus, now the 8, remember this I squared is going to become a -1. What it usually does is it changes the sign of that coefficient. So it was a +8, now it's going to become -8, which means I can combine my first and my last term. You'll always only end up with a complex number because you'll be able to combine the oi, the 2 middle terms, and the first and the last. So 6 minus 8 is a -2 minus 16i. That would be my final answer. Now let's look at what happens. Notice here I have complex conjugates. So we have the same thing, but one is plus, one is minus. And this is why complex conjugates are so important. So when I do my FOIL routine, I get 25 minus 10i. Then immediately I'm going to have plus 10i, so I'm going to write it right underneath there, minus 4i squared. So when I simplify this out, I've got 25. These two cancel. And remember, I squared equals a -1, which means it changes that sign. So this becomes plus 4. So multiplying complex conjugates together eliminates the imaginary part and just gives you one integer. And that's why those complex conjugates are really powerful. So let's go ahead and kind of formalize that concept. So a plus bi, a minus bi are called complex conjugates. And when you multiply them together, which is what we like, you end up with a squared plus b squared. Unlike when you did a difference of squares and you got a squared minus b squared, because that I squared is a -1. This is because I squared equals a -1. It creates a squared plus b squared. So it's really kind of powerful for simplifying your denominators, because just like radicals, you're not allowed I in the denominator. So let's see how we would deal with this. So in this first one, simplify -3 over 7i. Everything there is fine, except you can't have I in the denominator. So what we're going to do is we're going to multiply top, I'm going to make these a little bigger, top and bottom by I. Why would I do that? Because I have -3i on top, which is okay, just like radicals on top are okay. On the bottom, I now have 7i squared, which we know we can replace with a -1. So this becomes -3i over a -7, and all my negatives cancel. So we just have 3i over 7. Kind of a nice little trick. All right, so if you can get your I to be an I squared, then it will become an integer. Now, this one's a little bit, our next example, notice I've got I on top and on bottom. So on top is okay, so we focus the one on bottom, but it's embedded in a complex number. So here is where we multiply both top and bottom by the complex conjugate. So we multiply top and bottom. Since this was a plus, we use the minus. That means on top, I'm going to be distributing. On the bottom, I hope that you guys can get straight to the shortcut. So when you multiply complex conjugates, it's the first term squared plus the coefficient 5 times 5. So 5 squared, because remember the I squared is going to make that -25 become +25. So that goes really fast. Then on top, what do we have? 3 times a -2i, which is -6i. And then -5 times a -2 is +10i squared. So we can simplify that still. So this, remember, becomes a -1, basically makes that negative. So that becomes a real number. So that's -10 minus 6i over 34. Now, you might think, oh, we're done. But this really, we always want to reduce to lowest term. Notice that everyone here is an even number. That means I can factor out a 2 from the top and a 2 from the bottom. So if I factor out a 2, I get -5 minus 3i. So those 2's can cancel, and this would be my final answer, -5 minus 3i over 17. Be careful to factor it out of both terms. The biggest mistake people make is they only do the 10 and the 34. And you can't forget the 6, because that's just not nice. All right, last one. Maybe you should try this one on your own, okay? Because we want to get rid of the I, but again, it's only the I in the denominator that bothers us. That's our problem child. So we're going to multiply top and bottom by 1 plus I. That would be the conjugate. And then we have to now FOIL on top, FOIL on bottom. The bottom is the first term squared plus the coefficient, which is a 1. So 1 plus 1, that will become our denominator. On top, I'm going to have to FOIL this out. So I have a 2, I have a 2i, I have an I, and we have I squared. So simplifying this out, I squared gets replaced with -1. So 2 minus 1 is 1, plus 3i on top, and on the bottom we just have 2. And that would be your final answer. All right, so I hope you enjoyed working with the complex numbers. It's kind of cool, especially if you're going to be an engineer of any sort. You will definitely be using these.